Hello everybody, so this is Eloy and Goran from EffectiveTDs, and we just recorded a tutorial where Eloy is showing me the new feature in TP called APF, all-purpose fields, which are basically volumes that you can generate inside thinking particles and apply any kind of data, float and vector data, and then use that data to either move particles or do whatever. We don't even know the possibilities, like that's up to all the users now to figure that out. But what is really amazing is that we can actually do this in Houdini as well. And I was thinking, why don't I show Eloy how to recreate what we just did in Houdini, in TP, and I recreated in Houdini. And then we start comparing like the strengths of both softwares and actually how similar that whole workflow is. So let's start. What do you think?
Yeah, sure.
Are you curious to see Houdini?
Yes, I see it sometimes, but I would like to see, yeah.
Okay, so basically all I'm doing is I'm generating one geometry node, which is just the usual workflow in Houdini. And I'm just going to create a box. So that box is going to be
your APF.
No, well, for now it's just a box, right?
Okay.
And the dimension are going to be 100, just so we're matching exactly what we had in Max over there. To generate the volume like you did, all I have to type is volume. And now I have a volume grid over here. And if I middle click, Houdini always gives me information about the data that I'm working with. So I can see it's 1.1 primitive and 1 volume. And whenever you have a volume, you always have a point in the primitive because that's how it internally handles that. So now...
This means already it's a VDB now?
It's not a VDB, it is a volume. So there's two types of volumes in Houdini. There's the VDB and all original Houdini volumes. And the difference is that, well, it's just basically internally how it processes it. It's different. And the main difference is that in VDB, you can in the end save only voxels that actually have data. And VDB has a mode which is called sign distance field, which doesn't give you a data of a value. It gives you a value, but it's not like how much density or what is the vector in that field. It tells you how far am I away from the surface, which is what we saw, like the mesh distance in TP as well. It's just called an SDF. So if I would create a VDB from polygons, what it does, it generates a SDF field, and because we have such a big box, it just started creating, because the default voxel size is 0.1. So in Max over there we had 10. So now we can see here we have, well, that box is 100, 100, 100, and then it creates a VDB.
Wait, the size is 150 now on the VDB.
Oh, of course, because VDB always creates exterior band voxels. So if I go here, that's why. So if I go here and I look at my box, so you can see the original line of the box when I do the templating. And basically it created a SDF field around that box. And each voxel says, am I inside and how far am I away from the surface, or am I outside, which are these values here, which are negative. I'm not sure if it was negative or positive values. One is negative, one is positive. Anyways, and then you have here the exterior band voxels, which say how far outside and how far inside do you go from the actual surface. So if I set this to 1, you can see the box is decreasing. There you go. So 3 voxels, 2 voxels, 1 voxel. So it gives you only 1 voxel outside and 3 voxels inside. So that's basically the SDF, and it's called a sign distance field, so distance VDB. We can also switch that to a volume, and now we're actually having a proper volume. So if I set this resolution higher, we can see here that it is a real volumetric data. And now it actually filled, it also filled, I think it filled the whole box this time because it's fog density. Right. Okay, anyhow, let's go back to the volumes. So now I'm creating a volume, and the next step would be to give this volume a vector on the x-axis to the right, so all our points will move to the right, the same way we did in tinted particles. So what I can do is I can create a volume wrangle or a volume VOP. Let's go simple with the volume wrangle. So I go vol wrangle, and there we go, there's a wrangle. And now the wrangle lets us access, basically what it does, it loops through every single voxel of every single field that comes in here. So what we can do is we can say v at vel, for example, and actually we cannot do this yet because we didn't define what type of volume we have. We only created a volume, but we didn't define what it is. So first of all, right now it's a scalar field, so it only accepts one value, one float value, not a vector, and we didn't give it a name. So if we give this a name called density, for example, we can go here and we can say f for float at my own attribute density equals 1. And if I do this, you can see now all the voxel have the data of 1.
Okay.
Yeah. Now I can go say random random v at p, and now every voxel is going to get a random value based on the position. And you can already see it gives you random values.
How do you define the range of these random values?
Random functions always give you a range of 0 to 1.
Okay.
Always in Houdini 0 to 1. Okay, but now we're interested in a vector, right? So what we want to do is we want to call this, let's say we call it, let's call it wind. Usually we would call it vel for velocity, but we'll just call it wind. So now I can say v for vector at wind, my attribute, my field called wind, equals, and then we just set a vector which is on the right axis. Now
the only way to display this is with the fog? There is other ways to display?
There's other ways. So what I can do now is I can just scatter points. Let's just put a scatter. Let's see if that works. So we're scattering points inside this volume. So the scatter is just like an emitter. And if you give it a volume, it scatters inside the volume. If you give it a surface, it scatters on the surface. And keep in mind, we are still not in a dynamic system like TP or Fume or anything. This is still genome style. Every single frame gets recalculated without knowing the history. This is called the sub-level. Okay, so we're generating this field, and because nothing is animated, if you click here, Houdini knows that this is time independent. Says here time dependent, no. So even though this is reevaluating every frame, or it would be if something would be animated, because there's nothing animated, it knows I have calculated this once. This is time independent. I'm not gonna recalculate it, so I can scrub very fast.
That's cool.
Yeah.
So you can force this as well to
evaluate
on each frame.
Yeah. And it does that automatically the moment you start changing. So if I say my size is growing, so let's say, actually let's just say $F, which means frame. So on frame 1, this size is 1. On frame 2, this size is going to be 2. And now if I middle click, it automatically knows time dependent, yes.
That's very smart.
Yeah, it is. Houdini has really cool stuff integrate it into its like generic workflow. Okay, so now we have our points, and basically what we can do now is we can add a volume trail, and the volume trail takes geometry points and asks for a volume. So you can see required velocity volumes. So we can take a velocity volume, and you already see it starts drawing some splines here, but we need to give it the wind attribute. Okay, it already had it correct. And basically we can give it a trail length, and you see it starts generating lines along that vector. And what it does is actually it doesn't just show the velocity of each voxel, but what it does is internally it has a for loop. So it is gonna simulate a for loop, can exactly show you what the particle is gonna do if they start at this position. So it's gonna do, in the first loop, it's gonna say, create a piece of spline from this position onto the width by the vector, and then in the next iteration of the loop, it's going to look up the volume here, and it's going to create a new spline. So if this vector here would be different than here, it would start moving into this direction and go on. So if I go here and say f at wind equals rand, rand v at p, now every single value is going to be random. But we also need to, actually let's just put a random on all the three axes. So v at p, and Houdini as well, it knows if you're defining a vector attribute and you put a random function, it automatically creates a random vector value instead of a float value. So it just automatically does that. And now you can see it created a random random force basically. They're all pointing up because the random is based on 0 to 1, so it doesn't go -1. So they're all going kind of, you know, positive, positive, and positive.
How do you force to change the range of the random?
So what you would do is you would go fit 0, 1, and the fit is like the value to value node in TP. Basically it says I'm getting in a value of 0 to 1, and I'm gonna output a value of -1 to 1, or whatever value to whatever value you want. And the moment I hit this, this did not work, and that might be because it could be that it wants actually a vector. So what we would have to do is -1, -1, -1, and then here we want a 1, 1. There you go. So now all the vectors are random, and if I keep dragging this longer,
you have no other way to do that than with expressions in.
No, you can do it the same way as you would do it in TP. So there's called wrangle, and the other one is called VOP. So if you want, we can quickly regenerate exactly this thing in a TP fashion. So let's do this.
But maybe we can do the value-to-value example that we did in TP instead of the random value. Let's say bottom right, top left.
And let's do this without a wrangle. Okay, let's do exactly that. So we do volume VOP, which is basically the same thing we just had as a wrangle, but with nodes. And the cool thing is, if I create, let's say I create a fit, so the same function, right? It was fit 0, 1, we just call it fit. So fit asked for input and outputs. There's also a function in the vex.
It's exactly the same as value to value.
Exactly the same thing. It just doesn't have a graph. The graph you have to add yourself. But the cool thing is about VOPs is that you can go here, view vex code, and now you see that exact code that we did right before with the, well, we didn't connect anything yet, so it's not creating the code yet, but basically it gives you all the code that you would have to know if you would use a volume wrangle. So that code and this code is the same. All of this, like this predefined stuff, that is just like this node and all the whatever. But if I go now and I bring in my field, I have to bring in what I did with v at wind. I have to do that inside here, which is called the bind node. So the bind node does v at wind, and it brings in our vector field. So here, sorry, that's a little mistake from my side. We don't want to read it, we only want to write it. So what we do is we do a bind export. So now we're exporting to the wind variable. So vector. And now we can say, okay, I want this float to vector. Houdini is not as good as TP in just automatically converting vector to floats. So, but we did exactly the same thing.
That's so lame.
Coming from Houdini. Of course. Well, it does some stuff.
It can convert integers to floats, and
yeah, it can. It's just like, it's better, you know, the workflow is just you do it yourself. And what we want is, we want a minus, so we need vector to float, the same thing that we did in Thinky Particles. And in Houdini, the y is the up vector, not z. So we're taking y and we're saying minus 50 to 50 goes from -1 to 1, right? And we're putting that in. One thing that is happening is that this scatter is based on density, and it takes the density from the whatever first point from the first field it finds. And for us, the field is positive on this side but negative on this side. So whenever it's negative, this means like don't create any points. So to quickly overcome that, let's just put one in here, and let's just put the points there. So there we go. So now we have our points, and we can say, you see, go left on one side, go right on the other side, and the colors again giving us the speed.
I like a lot the representation with a volume trail.
Yeah. What you can also do is, instead of volume trail, you can actually create a volume visualize, and the volume visualize smoke shows it as smoke values. So you can take, well, we will have to give it some kind of thing for density, but you can use, let's try this. You see, it gives you the color of the actual direction. So X is always red. It would be blue if it would go on the Z direction, and green if it would go up. Yeah. Okay. And density again is, because it's positive on this side, it gives you, you know, X, but nothing on the bottom. Okay. So now we have our field, our APF. Of course, it takes a little long to create when you have to explain everything, but you get really fast at that. So what we want to do now is we want to create our particle system and move our particles. So what we do is we just create a pop network, which is a DOP with a pop object and a pop solver, pop for particle operator.
Now here we are time dependent.
Now we are time dependent. So we just entered a new context inside Houdini, and we have our source, and our source by default creates points on surfaces. What I'm going to do is I'm going to say all points, meaning each point generates one particle on every time this impulse activation is 1. So what I can do is I can say $F for frame, the current frame, equals CH for channel, and then we just say, we go one level up, and then we say start frame. I'll explain what that means in a second. So now, if we look on frame 2, this is 0, but on frame 1, this is 1, right? So on frame 1, there's an on input. On frame 2, there's a off, like a Boolean 0.
Okay.
And this here, channel up start frame, slash start frame, means I'm gonna read the channel, which is a parameter, which is any of these guys are a channel. So those are all ch, or if it's a string, it's a chs. So that means a channel or a parameter. And then it says, where do you get that parameter from? I'm going to, and then give it the path, right? And then you go, well, it's like in DOS, in old DOS or in Linux.
Yeah.
You go dot dot means go outside of myself. Dot means myself. So if I would go dot, that would mean a channel that I have. So for example, seed. So I could go, well, I don't need the dot. I could just go seed. And you see it already gives me that channel, which is this guy. But if I go dot dot slash, it goes outside of itself and then it goes one level up, which is this DOP solver, DOP network. And then I start typing start and it knows start frame.
And
okay.
It's 42. Nice.
What?
It says 42 as the default value. That it's the value, the response of everything in life on the book.
Really?
Yeah.
Okay.
42 has the meaning of, it's kind of a jig.
I didn't know that.
Yeah, it's a book, I don't know the name in English, the Otoscopist, Intergalactic Otoscopist,
right.
How you call it in English?
I don't know.
So at the end they look the response for everything, and the response to everything in the universe is 42. And
interesting.
Yeah, when you see a lot of...
I never noticed that. That's amazing.
I explained you something about Houdini that you didn't know.
I love learning something new every day. Unexpected. But anyways, so you see there's a parameter start frame on this node.
But I have a question, because all this is to give an on in a specific frame.
Yeah.
But you cannot simply say add the frame directly here, say 1.
Yeah, you can.
Instead of that?
You just say 1.
Will be the same?
It's the same.
You are overcomplicating too much.
Well, the thing is that this node, a lot of times your shot is not starting at frame 1.
Okay.
And it could be any frame, right? And then it's just easier to...
Okay.
Well, sorry, it's a habit that I picked up.
Okay,
so
no, it's funny. It's like
I fell into your trap.
In TP, I do the same when I need to create something on the first frame of my simulation. I create an on a neck timer.
Yeah.
So then automatically on the first frame will evaluate once. So
nice.
Whatever you are on the timeline,
it doesn't matter always.
When it evaluates the first time, it creates an on signal and then stops.
Okay,
it's the same as what you are doing accessing the...
That is smart.
Yeah.
Okay. Well, the cool thing is, okay, now we have our particles and basically they're not doing anything because we didn't give them any force. They would inherit velocity if we would give these points a velocity, but we didn't give them any velocity. So they're just static. But they're basically particles and they're getting age and all of that stuff. Actually, I can show you this by going here, geometry, and I can show you age, and you see they're all aging. Okay, anyhow, now I can use a pop advect node by volumes, and I could just plug that in here, and now that advection node asks me where do I find the field, the APF or volume field, to advect your particles from, and what field do I want to use for that. So you just go one level up, and we want one more level up, and now we have what was it called?
It's not your box?
No, it was the VOP, right? It was the volume VOP. There you go, volume VOP 1.
Okay.
And the field that we want is called wind. And now, you see, the particles start moving.
Yeah.
One problem that we're having is that these particles there's some of them outside of the volume, so they're not moving.
Makes sense.
Yeah, but basically this is your thing. This is exactly the same thing, and if I increase the velocity scale, this is now the multiplication of the force based on velocity. There we go. The cool thing is you have the option of do whatever type of force you want. You can even go and you can create a pop-wop here. Pop-wop. And now you have that same thing that we had on the upper level, but for your particles. And you can go and say volume sample vector. And we can say, what do you want to sample? I want to sample the input 2 of this node. Or basically, sorry, wrong. I want to sample the input 2 of this pop-wop, and here I can define what is input 2. So I can go level up, volume wop, and I can say, well, from this I want the wind, and now I can use this wind as a force here, or I can add any kind of modification on top of that. So I could combine it with whatever I want in a TP fashion after I'm reading the velocity from the volume.
We can do it in TP as well.
Okay.
We didn't do that, but as well.
Yeah. But you see now it still does it even though this guy is not even doing anything. Which is, I think it's very cool. Yeah. So this is the way what we did in TP. We can do it in Houdini in a different way. Yeah.
Cool. So next step will be
more complex APFs.
More complex APF.
All right, let's bring it on.
Yeah.